Okay, so demand controlled ventilation is in a lot of ways just what it sounds like. So just a little context first. So the commercial code, as we mentioned before, requires continuous ventilation for occupied spaces. And now our new residential code requires continuous ventilation, but those aren't really being necessarily interpreted or applied. They're not required to be applied in the same ways. This is something that's been long-standing in the commercial world, so it's taken a little more seriously, if you will, or there are more assurances that that will happen. So, you know, in other words, in the residential code, if they say, well, you've got to have continuous ventilation, but you can achieve that with your kitchen and bathroom fans, you know, a lot of people are in the end, they're not going to run their kitchen and bathroom fan 24/7. They're going to turn it off, and then there's no continuous ventilation. The convention has always been to have, during the occupied period, and sometimes 24/7, have your fan run continuously, and then have a fixed minimum outside air % by volume that's determined based on design maximum occupancy. So if the amount of ventilation air you need to provide is based on how many occupants you have, for a long time, the way they would deal with this is they just say, okay, well, what's the most people you're ever going to have in the space? Determine a ventilation rate based on that, and say, okay, then we'll just provide that all the time, so that whenever the space is fully occupied, there's enough ventilation, and when it's not fully occupied, there's more than enough ventilation. That's good for occupants as far as air quality, but it's not very good for energy. So, you know, a good example would be like a movie theater or auditorium, where your max occupancy could be anywhere from 100 to 10,000 people, you know, depending on the kind of venue. And if your baseline is 10 CFM per occupant, then that means 1,000 to 100,000 CFM of outside air during all those occupied hours. But those types of spaces, libraries, auditoriums, theaters, conference centers, things like that, they tend to not very often be fully occupied, and they tend to go in, like, you know, from nearly fully occupied to zero, to nearly fully occupied to zero on relatively short periods sometimes. You know, you might have a 3-hour morning session, and then 3 hours nobody in there through lunch with an hour on each side of lunch, and then in the afternoon you got an afternoon session where it's nearly fully occupied. So in the old days, that air handler would just provide that enormous amount of ventilation air all day, maybe all night, even when there's nobody there. So how can we do better than that? And again, we looked at on Wednesday at how, you know, there's some fan energy implication there, but mostly it's about all the energy to heat or cool that ventilation air to make it maintain comfortable space now. So demand controlled ventilation is how we address this, and you use either occupancy sensors, or more commonly these days CO2 sensor, to determine whether or not the building is occupied, or the space, and then based on that decide to what degree, or it might not be a binary decision. You might not just say occupied or unoccupied. You might say, well, it's occupied, but it's not at peak occupancy, so we can modulate that ventilation rate somewhere in between the minimum and maximum. And CO2 is a good one because, you know, as we breathe, we're all exhaling CO2, a certain amount of CO2. And so the more people you have in a space, the more CO2 you're going to start to accumulate in the space. The more people you have, or the less you're meeting the ventilation requirement, right? So if you get more people, or if you're not ventilating enough, you're going to see the CO2 rise. Okay. So you use a CO2 sensor, and you monitor the CO2. But I'll back up. So without CO2 sensor control, you can do it with occupancy sensors. So one example of that is these systems that we're seeing that are becoming more and more common in hotels. Like, you may have seen this exact thermostat if you stayed in many hotels recently. This is Incom. It's made by Honeywell. It's a thermostat like any other. It's got you know, 2 little buttons to adjust your set point up and down. It's got a button to turn it from off to auto, a button to change the fan speed, and a button to change what you can see on the display. But down here in the lower right corner is a motion-based occupancy sensor. So this thing it's trying to determine if anybody's in the room. And if nobody's in the room, it'll set the set point back, and it'll turn the fan off or switch the fan to off. And then when somebody comes in the room, it'll bring the set point back up to the occupied set point, and it'll make the fan run in continuous on mode.
It'll allow for manual adjustments also.
Manual adjustments, yeah, anytime you're there, you can adjust just the set point and the fan mode and etc. But when you're not there, it goes to its occupied mode. Yep. So this is a purely occupancy-based method to do that. So usually this is tied to a system that doesn't have like a modulating outside air damper. You know, it's got a fixed minimum ventilation rate. But if you turn the fan off when nobody's there, you know, you might get a little leakage through there based on, you know, building pressure differentials and things like that. But you're not going to be driving ventilation area with the fan. Okay. But a better approach is to use a modulating outside air damper and a CO2 sensor. And the CO2 sensor can be, you know, if you've got one air handler that serves a lot of different spaces, you could put a CO2 sensor in every space. That's costly. If you put a CO2 sensor in the return duct that pulls return from all those spaces, you're effectively getting an average CO2. So that doesn't ensure that you won't still underventilate. If you've got one room out of 10 that's at like peak capacity and all the other 10 are empty, your average is going to look fairly low. You might still underventilate in that room that's at peak occupancy. So usually it's a hybrid approach where you say, okay, we'll put a CO2 sensor in the return air, but then there are these several zones that we know tend to be more occupied than the others. We'll just put wall-mounted CO2 sensors in those zones. And you monitor the CO2 continuously, and if that CO2 level gets above, the typical set point would be 1,000 to 1,200 parts per million of CO2. Then you start to open your outside air damper more and bring more ventilation air into the space until you bring that CO2 back down to that below that set point. And like any set point, you typically have a deadband. So, you know, if your set point is 1,000, and you might say my deadband is going to be 100 CF or 100 parts per million on either side of that. So if I hit 1,100, I'll start opening the outside air damper, and I'll open it until I get down to 900. Then I'll start going the other way.
Makes sense.
The one thing that's often missed in this strategy, a couple things. For this, this could be a good thing from an occupant and occupant ventilation standpoint. Regardless, it can be a good thing. It's like, okay, you've got controls in place to ensure that you're matching your ventilation rate to your occupancy. That's good. If you expect to get energy savings out of it, like especially in a retrofit case, there are a few conditions that have to apply. First of all, you're not going to get any energy savings if you weren't over ventilating before. You know, the savings here comes from not over ventilating. So you have to be sure that before the CO2 sensor and the associated controls are installed, you were putting too much ventilation air in space. And then when you put the CO2 sensor and the other controls in place, you need to make sure that you don't continue to do that. And you know, once you have the CO2 sensor, the demand control ventilation in place, that minimum damper position that used to be at a fixed 20% or whatever to always provide that ventilation rate for peak occupancy, you need to which was always called minimum, even though it was for peak occupancy. It was like, it's the minimum ventilation we'll provide based on if the space were fully occupied. Because we didn't, that was, you know, you weren't modulating that outside air damper based on ventilation demand. So after you put your CO2 sensor in, you need to say, okay, we were at a 20% fixed outside air damper position. Now we need to allow it to go more close than that if there's no call for ventilation. Otherwise, you don't save any energy. And what I see happen often is that they'll put the CO2 sensor in, and they put the programming in, they don't make any change to the minimum position on the outside air damper, and so it sits at the same place it always was before anyway.
But they're at the cost of a CO2 sensor.
Yeah, and the install, and you know, and a typical cost for DEC points installed is anywhere from $300 to $1,000 a point. You know. And on this, if you were to have a controls contractor come in to do demand control ventilation on one air handler, where they have to put in a CO2 sensor, maybe several, but then also do like a couple hours of programming and a few hours of making sure it all works, you know, you're $10,000 into it before you know it. And if you didn't make it work right to actually save energy.
The payback time's quite extended if you don't actually implement the changes.
Yeah.
Yeah, I suppose. Okay, makes sense.
Exactly. So here's a good schematic that I found that I stole from the web. So here's an example. So here you're at full occupancy. You've got a bunch of people in space. You've got a CO2 sensor in the space. It's reporting CO2 level to the control panel. The control panel compares that CO, and actually they show this label says CO, even though this one over here says CO2. It should be CO2. Anyway, it makes a comparison of that CO2 level to a set point, and then it just makes decisions about how to control this exhaust air damper and this outside air damper to bring in more fresh air. And then when there are fewer people, the CO2 level will go down, and it will modulate the outside air damper more enclosed. So here in this case, you might be getting, they say 200 CFM outside air, in this case 120. So it's a good measure when it's applied properly. And so, you know, with these new codes that require continuous ventilation in residential buildings, for example, we talked in the last lecture about how, you know, you might have a 3-bedroom, 1,600 square foot house that the new code would require 60 CFM continuous ventilation. We should look for ways to avoid these same mistakes that were made in the commercial sector for so long before they started doing demand control ventilation. What I see with a lot of the HVAC and control stuff in residential is it lags way behind commercial. And if we could just get those people talking to each other a little bit more and say, well, you know, in the commercial world, there's an easy solution for that. We just do this, you know. Then we make some quicker strides toward greater efficiency.
And then there would have to be a summit and a get together, and you would have to.
Actually, you'd be out of a job if more people took that advice.
No.
I don't think so.
No. I mean, I wouldn't. If what I do in the commercial world made its way into the residential world, that doesn't impact me at all.
Might even start a side business and make even more money.
That's the truer words coming from stroke. I mean, that's.
Yeah, it's, you know, you always want to learn from.
There's an altruism there.
Yeah, learn from what other people are doing in a slightly different sphere that's related. Yeah. Okay, so economizing cooling. This is another one. This has been very well understood and you know, even code required by code in the commercial world. There is no requirement for this that I know of in the residential sector. But you know, if you're going to have an air handler, and that air handler is responsible for some ventilation, and you can go a step further and have a modulating outside air damper with a little bit of control to be able to make use of that outside air for cooling when the space needs cooling. It's a good thing, right? It's a lot less energy intensive and therefore less costly way to cool a space than to run compressors on an AC system or run a chiller or something like that. So the concept is you need an outside air temp sensor and you need a return air temp sensor or a space temp sensor. And if the outside air is cooler than the space air and you need cooling in the space, send some outside air into the space, right? That's a pretty simple concept. It becomes more complicated if you want to do, like, especially in more humid climates. We see this here sometimes, but in my opinion, it's not worth the extra cost. But in more humid climates, it can be worth the cost to do what's called enthalpy-based economizer, where instead of just comparing outside air temperature to return air temperature, you compare outside air enthalpy to return air enthalpy. So you're taking account of the latent heat that's in both air streams. And basically that means that you're measuring temperature and relative humidity, calculating enthalpy from the two, comparing the enthalpy values, then decide if the outside air enthalpy is less than return air enthalpy, then you can economize.
But again, that's more for tropical type zones.
Not necessarily tropical, but Seattle at the least, you know Boston, Seattle, and then any place more.
When I say tropical, I mean
You're talking
more humid, hot.
Yeah, more humid than
more
here.
Hot and humid.
Yeah.
No, just humid.
More humid, yeah, more humid than here.
Because Boston's not too much warmer or
Certainly
colder.
not, certainly not tropical.
Yeah.
No,
Yeah.
but I was thinking like.
But yeah,
I was thinking like St. Louis.
Yeah, absolutely, absolutely. Yeah.
It's 100 and 100.
Yeah, yeah, because in climates like that, I was doing a project down in Tulsa, Oklahoma a couple of years ago, and this is a great example of that. You could have outside air that's cooler, temperature-wise, that's cooler than your inside air, but because it's so much more humid, you do not want to bring that outside air in to try to cool the building. It has the opposite effect. So, but in our climate here, you can get away with dry bulb economizer. It hasn't been common in residential because historically there was no active ventilation system in the home, except maybe beyond the bathroom fan whenever you turn it on. But, and we're still transitioning, so, you know, we still don't have like full-on air handlers in most homes like you have in a commercial building. But if we start to see furnaces where you have an outside air, you know, ventilation air intake into the furnace, the next step then is to put a modulating damper with a motorized actuator and some controls to allow that outside air into the furnace when you want it, and to close it off when you don't want it, or to modulate it in between.
Makes sense.
There are a lot of furnaces out there that do have AC in them with no outside air, and so that they can't economize. They're just going to run the AC when there's a call for cooling. You can also have a separate system that does the economizer.
Just run the fan only.
Well, again, a lot of furnaces don't have any outside air ducted into them. And so even if you run the fan, you're just recirculating inside air. So there's no potential for that there either. So here's an example. This is, again, a screenshot from a building automation system, different project. This is a packaged rooftop unit. I should have put a picture of it in here since they don't look anything like the schematic, but you know, it's just a big metal box sitting on the rooftop. But it has an outside air damper that has a little electric motorized actuator on it, as is shown schematically here. It's got a return air damper with its own actuator. It's got a fan. It's got a direct expansion AC coil for air conditioning. This is a cooling only unit. There's no heating coil in it. This is a filter bay over here. And it's got temperature sensors, so I can see what the discharge air temp is. Right now it shows 59. I can see that the return air is coming in at 66.7. Outside air right now is 60.3. So I can see also that the zone temp is 68.7 and the zone temp set point is 68.4. This unit doesn't have a very wide deadband. It's basically as soon as you get, oh, you know what I think is going on here? I'm sorry. This is, yeah, so we're just barely above our cooling set point, but I think probably this started to cool when that gap, that delta was greater. We're just seeing it near the end of its cycle, so it's probably about to stop cooling. But in any case, we do have the zone temp above set point, and so you can see right over here it says it's commanded the economizer to 100%, which means 100% open outside air damper. So that would also mean it's closed the return air damper. So right now it's not recirculating any room air. It's just bringing in 100% outside air because the outside air is cooler than the return air and it wants to cool the space. And this 100% value here will modulate between 0 and 100% depending on, you know, when it gets a cooling call, it'll start to open it. If it gets to 20% open and the cooling is satisfied, it'll start moving back the other way. If it gets to 100% open and it can't bring the space temp down to set point, then it'll allow this direct expansion air conditioning to start running. But it won't allow that DXAC to run until it's at least given a chance for the outside air to do the cooling. Right. If your outside air is 60 like it is here, you don't have as much cooling capacity in the outside air as you do if it's 30. If you have 30-degree outside air, you probably don't need to run this AC at all. You can probably cool the space with 30-degree outside air. And in that case, you're going to have to mix it with a certain amount of return air. Otherwise, you don't want to have 30-degree discharge air dumping into the space because that's uncomfortable. Good. So again, I guess this is a reiteration of some of what I said before. Now that we see more of these supply air systems in residential, whether it's an HRV or an air handler or a furnace, you know, you can accomplish the economizer cooling if you make sure that you do have an outside air intake ducted into that air handler, whatever it is. You can do it by installing an HRV that's set up properly for this. And you can do it with a heat pump that has outside air ducted in from some intake. And the logic is simple, like I mentioned before. You compare your outside air temp to your return air temp, and you need the right controls to be able to make it happen, meaning some kind of controller that can do the logic, some kind of modulating actuator on your outside air damper. And on an HRV, what you typically need is a way to bypass the heat exchanger. There are times, if you don't bypass the heat exchanger and you have nice cool outside air, it's going to heat that outside air up in the heat exchanger before it delivers it to the space. So if you want to use the outside air to cool, you need to bypass it around the heat exchanger. through a separate duct with a bypass damper. Okay, so this is a new topic now, multi-speed or variable speed fans and pumps. Wherever you've got air or some kind of fluid as your heat transfer medium, which is any forced air system or any hydronic system, you've generally got a fan or a pump to move that fluid. And the old convention was to size a constant speed fan or pump to deliver full flow rate whenever it was needed, and then to shed capacity at low load or demand by either closing or throttling a three-way valve or a damper, and let the pump or fan do what we call riding its curve. I'll explain that a little bit more in a minute. But or you can cycle the fan or the pump, or cycle some bypass. Basically, you know, in the case where you're not cycling the fan or the pump, you've got the full flow of air or water moving all the time, and then you modulate these valves to either send it to your coil or your discharge point, or bypass and just keep it in the loop. But in either case, the fan or the pump is constantly working, you know, to move a full flow. And fan and pump energy are most directly correlated to flow rate. So if you double the flow rate, you double the power at the fan and the pump. So you get much better system efficiency if you can modulate the flow rate instead of taking these bypass or cycling approaches to dealing with matching your capacity to your load. Okay. There's a set of equations called the affinity laws, which apply for centrifugal fans and pumps. Don't expect you to memorize these, but I'll give you a little key here for what the different abbreviations are there. CFM, you know that one, RPM, rotations per minute. Pressure, P is for static pressure differential, which is also called the head. BHP, brake horsepower. It's just a particular, denotes the horsepower measured under a certain method of measurement is all. It's just the horsepower.
And you can use that with water horsepower too.
Yeah.
It's the same thing.
Yeah. And so we're most interested in this equation that relates the horsepower and the RPM. Okay, because what we're talking about is variable speed pumps or fans. If we change the RPMs, the rotations per minute, change the rotational speed, how are we going to change the power input to that system? So that's this one of those three equations. And so as an example, if you use this equation to look at the difference in brake horsepower between spinning at 100% speed versus 50% speed, okay, you can, that means that we're saying RPM new in this equation is 50% of RPM old. If RPM old is the initial 100% speed, and we're going to go to 50%, that's 50% of 100%. Okay, so we take that relationship there, plug it into the equation, do a little algebra, and you'll find that the new brake horsepower at the 50% speed is 1/8 of the old brake horsepower. So at 50% speed, we draw 1/8 as much power as we do when we spin at 100% speed. So it's not linear. It's actually cubic, and that's, I say here in theory, it's a cubic relationship. In practice, you don't quite get your full 7/8 reduction when you go to 50% speed, because there's some inefficiencies, some realities that come into play. But you get close.
Well, your power's down, but the efficiency of your motor and pump, whatever driving is not as efficient running as designed.
I'm impressed that you know that. That's something I see engineers even miss on a regular basis, like energy engineers, when they do these calculations of how much you save. They don't. So it's a really good point. So what he's saying is, this law applies to the fan or the pump itself, not the motor that's attached to the fan or the pump. Okay? And so even though you might spin your fan at 50% speed and only need 1/8 as much power at the fan, okay? Now you look at the motor. The motor is designed to, if it's this will make it, to make the math easy, let's say it's an 8 horsepower fan motor system. Okay? So at full speed, the fan needs 8 horsepower. The motor size is 8 horsepower, no problem. Now you slow your fan down to 50% speed, it only needs 1 horsepower. When you ask an 8 horsepower motor to only do 1 horsepower worth of work, its efficiency takes a dive. Well, it doesn't still output 8 horsepower. It only puts out what you ask.
But how much energy does it require?
Yeah, more energy has to go in per horsepower at 1 horsepower than at 8.
So that's where this law counteracts with the efficiency. This is in like energy storage and distribution 214. So,
but it doesn't. I'm looking for a trash can. This is where the variable frequency drive comes in as a really important part of this whole puzzle, because if you change your motor speed, you don't get that same severe drop in motor efficiency. You get a little bit, but not anywhere near. You know, I've seen motors a 50% loaded, I've seen 70% loaded motors that are running at about 60% of their peak efficiency. It takes a pretty sharp dive when you get down below about 70% load. But if you put what's called a variable frequency drive on the motor, this is a VFD right here on a big air handler. The variable frequency drive takes line voltage at 60 hertz in, and it takes that line voltage sine wave and it chops it up and digitizes it and spits it back out as a simulated sine wave of a different frequency. And when you send that new frequency into the motor, it changes the motor speed without impacting its efficiency very much. These are, costly. They used to be, I don't know what the going rate is these days. I guess it's, we used to say $500 a horsepower for these, but I think they were down, in some cases, closer to $100 a horsepower now. Prices come down a lot.
but it's not a lot when you think about
how much you save.
Yeah, so.
It's a great energy conservation measure to put a VFD on any pumper motor that has any diversity in its load requirement. For smaller motors where the VFD is not cost effective, what they're doing now is they're making these electronically commutated motors, or ECMs. That's basically a brushless digital motor, just like you have in your hard drive in your computer, or the cooling fans in your computer. And they're making these all the way up to like 1 horsepower size, or I think now they're even getting bigger than 1 horsepower. But these are becoming more common in newer residential furnaces, some other things. And so it's kind of like a VFD built into a motor. And you can vary the speed of these as well to maintain higher efficiencies. So in either case, so here's an example of what you would do like in the residential scenario with a 3-speed ECM. A lot of ECMs can modulate fully between, like, infinitesimally between 0 and max speed. But to simplify the electronics and the controls that interface with it, they'll just say, this thing can do just about any speed you want, but we're going to pick 3 speeds and give you not a binary, but you switch between 3 ranges of voltage output, and it'll just go to one of these 3 speeds. So in that scenario, like with a residential system, you could say, okay, if it's a heating and cooling furnace where you have AC in it, when there's no call for heating or cooling, it stays at its lowest speed. When you get a call for heat, it bumps up to the middle speed. When you get a call for cooling, it bumps up to max speed. This compares the old method with the new method, right? So this is like a hydronic system. So in the old style, you'd have this pump. Here's your boiler down here. You have a pump circulating on this loop, and you have a 3-way valve. 3-way valves have 3 ports. The water can't go 3 ways; it can only go 2 ways. But we call it a 3-way valve because it has 3 ports. That confuses people. Whereas this valve over here with 2 ports where the water can only go 1 way is a 2-way valve. Okay. So the 3-way valve, you're circulating around, right? If you get to this point, if you don't want heating at this heating coil, let's say it's baseboard radiation in the bedroom. If you don't want any heat in the bedroom, you just open this port down here and you send the water around it and back. Okay. If you do want heat in the bedroom, you open this port and you send it through. If you want a little bit of heat, you send some through here and you send the rest through here. Okay? But either way, you're maintaining the same flow rate through the pump at all times, more or less. There'll be a little bit of change. As this valve strokes, you see a little bit of change in the pressure differential. The flow rate changes a little bit. If you put a 2-way valve in here, okay, and you don't put anything on here to control the pump speed, when you run this pump now, if you don't want heat here and you start to close this valve, now the pump's just working harder to try to push through a more closed valve. Actually, I shouldn't say it that way, because it actually doesn't work harder, it works less hard. But it is pumping through a more closed valve. I'll show you that on a pump curve in a minute. But it's not the efficient way to do it. If instead you add a VFD or an ECM motor that can vary its speed, as this valve starts to close down, and you have some way to tell the system that the valve is closing because it doesn't want as much flow, slow the pump down and match the pump speed to the valve position, more or less, and vary the flow rate through the system. And now you get that affinity law comes into play. And like was said earlier, if you don't have a VFD and you're trying to do this affinity law thing, the pump just rides its curve and the motor gets partly loaded and your efficiency is lost because of the dive in the motor efficiency. But if you can vary the pump speed, you maintain your motor efficiency and you get a real payback. Okay. So here's this diagram. I won't go into too much detail, we're running out of time, but if you guys want to study it more, I thought it was a pretty good diagram. This is the 4 different ideas, right? So there's start-stop control, just cycle the pump. There's bypass control, which is the 3-way valve, where this is a bypass. Okay. There's throttle control, where you have this without the variable speed, so you're just throttling, closing this down and making the pump try to pump through a more closed valve. And then there's the variable speed control, and the bronze is wasted energy. You know, so if you do the variable speed control, you waste almost no energy. You get energy, everything goes to savings. In all 4 cases, you will, you know, if this is your design flow rate, this is like the flow rate you need at design conditions, and you're at a less than design condition, so you're trying to scale down your capacity to meet the diminished load. In every one of these cases, you'll go from design flow down to a reduced flow rate, right? But in all 3, other than variable speed, when you do that, there's some waste. And the greatest is on the bypass. So you'd actually do better to just throttle this 2-way valve without speed control than you do to bypass.
And just open the window.
But even better than throttling without speed control is to have some speed control on the pump. Okay, if this is the pump curve, you remember this? This is the system curve, right? Pressure versus flow. So if you're operating right here at this design point, design flow rate, design head, and you throttle, let me go down to the throttle one, what happens is it rides the pump curve, which means it stays on the pump curve and it moves to this lower flow point, higher head, lower flow. Okay. When you add speed control, instead of riding the pump curve, it rides the system curve. And it goes down to the same lower flow rate, but at a much lower head than it would be if it rode the pump curve up to here. So, anyway, bottom line, you don't need to remember all those little details, but this is the efficient way to do it. And you're not really dropping your motor load the way you do when you throttle or bypass, or start-stop is kind of a separate issue, but
Good illustration.
yeah. Okay, so the last one. Any questions on that pump and fan, speed control? So get ECMs, get variable frequency drives on those things. Now, places where it doesn't work are like constant head applications, like a well water pump. You don't want to put a VFD in a well water pump for savings. You can do it for other reasons. If you want to even out, usually what you have is a well water pump that bangs on off, and you got a pressure tank, and the pressure tank is trying to even out the fluctuations in pressure. You can put a VFD on the well pump and get the well pump to just modulate speed based on how much water you're asking for in your fixtures around the house, but it's not going to save you any energy because the lift from the bottom of that well stays constant. Or an elevator is another one, constant head. It takes the same amount of energy to pull that elevator up from the basement to the top floor, regardless of how fast you do it. Power changes, but you're not going to get any energy saving. But for things where you have valves or dampers on fans, generally speaking, there's not. In some cases, you have a better case than others to put variable speed on, but it will always save energy. It's just a question of will it save enough energy to pay for the retrofit. Heating water systems, hot water supply temperature reset. So this would be like in the residential case, this would be a boiler for radiant floor or hot water baseboard or a hot water coil and an air handler, which is not so common in the residential world, although I do see it. I have a friend in town here who's got an old ass, super old boiler in his basement with an air handler and a coil in it. But I think a plumber lived there beforehand. Anyway, the idea here is pretty simple. When it's cold outside, make a hotter hot water temp. When it's warmer outside, make a cooler hot water temp. You probably don't need 160 degree water to heat your house when it's 50 degrees outside, but you probably do when it's 0 degrees. And what these actual temps are, 120 versus 160, that depends a lot on not only your particular building and its envelope and its insulation and all that, but also when you size your hot water, let's say it's baseboard, if I think you're always going to run it at 180 degrees, I can heat your room with a 3-foot section. If I know you're only going to use 160 degree water, I might have to go to a 6-foot section. It depends on how much capacity you have out in your radiant floor or your baseboard or whatever. But regardless of what these two temps end up being, the point is you can probably put some distance between them based on outside air temp. So for controls, you're going to need a controller that can monitor the outside air temp and then make some decisions, some logic to tell the boiler what set point to maintain based on the outside air temp. You can get these little controllers, add-on controllers for a boiler system that will do that. That really, it's no more complicated than like on your automatic sprinkler system for the lawn that has a moisture sensor and says, you know what, it rained last night, I don't need to open the solenoid valve today. It's about that level of sophistication. So what, then do I have a couple more slides? So that's that same slide we saw last week, right, for a typical boiler system for residential, radiant or whatever. I don't know, this one I just threw in there because I had it and I didn't know if I was going to use it, but this just gives you an idea of like maybe a more complicated air handler, and this isn't even the most complicated air handler, but in a commercial setting, and how many points, each of these little white boxes is telling you something. It's either being measured or a command value in the controls of that system.
This is a screenshot.
Yeah, just a screenshot from that interface. And one thing I haven't mentioned, at least in this lecture, is also with these types of building automation systems, I can go in when it's live, I can right-click on one of these and tell that valve to open or close. I can override it and tell it to do whatever I want it to do, which can also be handy for troubleshooting. So they're pretty slick systems, and it helps too to have this schematic. You might go look at this air handler in its physical reality, and it's got snaky ducts all over the place, and the piping's all crazy, and you can't even tell which is the return fan, which is the supply fan until you scratch your head for an hour, studying over the whole thing. You get a schematic view like this, and it's like, as long as they got the schematic right, so it's schematically accurate, it can be a lot easier to figure out what's going on looking at this than looking at the actual air handler.
Well, it's also a lot more complex when it's just a table.
Yeah.
Of like 40 different set points and inputs.
Yeah, and we do still see a lot of the early digital control systems, and I mean, even a lot of them up until fairly recently didn't come with the graphics package. So that's all you would get is tables.
Yeah, and then you got to go.
Right,
and then it's, if they wired it right.
Yeah, that's my job, is to go through and test it all after it's installed and make sure that they did wire it right, and make sure that, like, now when you add graphics, you have the potential to accidentally pull the wrong point value into this field. So you might swap these two. So when I look at this, I think that you're commanding the heating valve open and the cooling valve close, but it's actually the opposite, right? So it's got to flush out all those little airs. That's one of the first steps in my job in these projects. Okay, any questions? All right.